Today we are going to start the new chapter, that is Unit 8, D and F block elements. First, let us discuss all the properties of D block elements. Now, we know that the D and F block elements, they are placed in group number 3 to 12 of the periodic table. So, D block elements, they are placed in group number 3 to 12 of the periodic table. And we know that the D block elements are also called transition elements. Now, in D block elements, why are they called D block elements? They are called D block elements because their D orbitals are getting filled. Now next, we can see how they are arranged in the periods. The D block elements, they spread across 4 periods in the periodic table, and the period number of D block elements starts from period number is equal to 4. So, we can find this D block elements in period number 4, 5, 6 and 7, and they are present from group number 3 to group number 12. Now, I have written here a table. That is, in the first column, we can see the period number. The period number. Second column, the name and the elements. Third column. Now, period number 4, I told you the D block element starts from period number 4. In period number 4, we have 3D orbitals getting filled. So, we can call that elements in period number 4, the D block elements in period number 4 as first transition series or 3D series. And we have 10 elements in the 3D series, and we have already learned these 10 elements. They are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. And also we know that this period number 4 elements takes the electronic configuration of the noble gas present in period number 3. And the period number 3 noble gas is argon. So, we have the inner electronic configuration of argon gas followed by the outer electronic configuration. And the 3D orbital is getting filled in 3D series. And you can also see the exceptional configuration taken by chromium and copper. Chromium configuration is argon 3D54S1 and copper is argon 3D10-4S1. And we have already studied the reason. They take this exceptional configuration to get extra stability due to half filled and completely filled d orbital. Now, there is the 10 elements, and this element scandium. Scandium is atomic number 21. Scandium atomic number is 21. Then, the last element of the 3D series, that is zinc, is atomic number 30. Atomic number of zinc is 30. Now, next we have the period number 5. In period number 5, we have the second transition series or 4D series. And again we have 10 elements in the 4D series. Now, I have written the element coming under scandium, and we know scandium is in which group? Scandium is in third group of the periodic table. It is in third group. So, this is group number 3, 4, 5, 6, 7, then 8, 9, 10, 11 and 12. So, I have written the element coming under scandium. Element coming under scandium is yttrium, YTTRIUM, and element coming under titanium is zirconium. Now yttrium electronic configuration is krypton 4d1 5s2, and you know that this is also called 4d series or second transition series because their 4d orbitals are getting filled. So yttrium has 4d1 5s2. Now zirconium, the next electron enters into 4d, which means the configuration of zirconium is krypton 4d2 5s2. Now the last three elements of this 4d series is palladium, silver, cadmium. Now palladium configuration is krypton 4d10 5s0, silver is krypton 4d10 5s1, cadmium is krypton 4d10 5s2. So these elements we have to study coming in 4d series, the first two elements and the last three elements with the electronic configuration. Now comes the next series, which is in period number 6. Period number 6, we have the third transition series or 5d series, and in third transition series or 5d series we have the element coming under yttrium, which is in third group, lanthanum, and under zirconium we have hafnium, 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 and lanthanum has the electronic configuration xenon 5d1 6s2 and hafnium xenon 5d2 6s2. We can see that the 5d orbital is getting filled. So they are called 5d series or the third transition series. Now the last elements coming in this series is platinum, gold Au, and mercury, that is Hg. Now let us see the electronic configuration of platinum. Platinum is xenon 5d9 6s1, gold is xenon 5d10 6s1, and mercury is xenon 5d10 6s2. So this is our third transition series. Now comes the last transition series, which is in period number 7. Now they are called the fourth transition series or the 6d series, where the 6d orbital gets filled, and we have two elements in, I have written in the 6d series. Coming under lanthanum we have actinium with electronic configuration radon 6d1 7s2, and next element is rutherfordium with configuration radon 6d2 7s2. Now this series is incomplete. Okay, so we have in the D block elements 4 transition series, first transition series or 3D series, second transition series or 4D series, third transition series or 5D series, and fourth transition series or 6D series, where the 6D orbitals are getting filled. Now we know the inner transition series, that is they belong to F block elements. We have two inner transition series, one is 4F series and the other is 5F series. Now this 4F series that comes from the 6th period, that is lanthanum, 14 elements following lanthanum whose 4F orbitals are getting filled. They are kept at the bottom of the periodic table and they are called the 4F series or first inner transition series. Now next we have the 5F series or second inner transition series, that is the 14 elements following actinium in 7th period, whose 5F orbitals are filled and they are also kept at the bottom of the periodic table. So we can find these F block elements at the bottom of the periodic table, and the F block elements they are actually from period number 6 and period number 7. But their F orbitals are getting filled, so they are kept at the bottom of the periodic table. So I told first we will discuss about D block elements, that is the transition elements. So this is the transition elements, and you should be thorough with the electronic configuration and the elements that is written on the board. Okay, the first transition series you should be thorough with all the 10 elements with their electronic configuration, which I have already studied. You remember the electronic configuration of scantium. Scantium is argon 3d1 4s2, titanium 3d2 4s2, vanadium argon 3d3 4s2, then chromium is argon 3d5 4s1, manganese takes argon 3d5 4s2, Iron, argon 3d6 4s2, cobalt 3d7 4s2, nickel 3d8 4s2. Then we have copper taking configuration argon 3d10 4s1. Finally zinc with 3d10 4s2. So with zinc all the 3d and 4s orbital gets completely filled. Now next let us see. Now this chapter we will study this chapter as question answer model. Okay, so first let's see about D block elements, the properties, the various properties, the reasons for these properties exhibited by D block elements we will study. So the first question is, D block elements are called transition elements. Why? Because we know that the D block elements, their position in the periodic table is between S block, which are very reactive metals, and P block, which are reactive non-metals. That is, when we move from left to right of the periodic table, there is a transition from metallic to non-metallic character, that is mainly through D block elements. So we can call these D block elements as transition elements. Now the second question is, can we call all these D block elements as transition elements? The answer is no. Now which all elements can be called a transition element? Only if that element has, there are two conditions to call an element a transition element, and the two conditions are the elements should have an incompletely filled d orbital. So that is the first condition. Element should have incompletely filled d orbital. That is, incompletely filled d orbital means what? There should be unpaired d electron. So you can call an element a transition element if it has incompletely filled d orbital in the ground state or any of its oxidation state. Now these transition elements can show wide range of oxidation state. So either in the ground state or in any of the oxidation state, if the element contain an unpaired d electron, an electron which is unpaired in the d orbital, then we can call that element a transition element. Now let's see the next question. Zinc, cadmium and mercury. Zinc, cadmium, mercury. They are not considered as transition elements. Why? Why are they not considered as transition elements? We can see that the zinc, cadmium and mercury, you can see here they are coming in the last. Zinc, cadmium, mercury. They are the last elements of each transition series. And you can see their D and S orbitals are completely filled. So we can write their electronic configuration as the zinc, cadmium, mercury has the general electronic configuration N-1 D10 NS2. Now we know N-1 D. N-1 D means it is the inner d orbital. Okay, so the electron is entering into the inner or penultimate orbital. N-1 is the penultimate orbital. So the electronic configuration of zinc, cadmium and mercury, general electronic configuration is N-1 D10 NS2. Now you can see that they have completely filled d orbital in the ground state as well as in their common oxidation state. The common oxidation state taken by these elements is +2. So +2 means 2 electrons from Ns orbital is removed. So what will be the configuration? It will be N-1 D10. Again, there is no unpaired d electron. So you cannot consider zinc, cadmium and mercury as a transition element because there is no unpaired d electron in ground state as well as in the common oxidation state. Now the next question is question number 4. Scandium is considered as a transition element but zinc is not. Now how can we give the answer? Scandium, the electronic configuration of scandium is argon 3d1 4s2 and zinc electronic configuration is argon 3d10 4s2. Now the question is, scandium is a transition element. Why scandium is a transition element? Because scandium has incompletely filled d orbital in the ground state. You can see there is only one electron in d orbital. Whereas zinc does not have an incompletely filled d orbital in the ground state as well as in the common oxidation state. Now question number 5. Silver has completely filled d orbital in its ground state. How can you say that it is a transition element? So the question is, silver has completely filled d orbital in its ground state. So let's write the electronic configuration of silver. Electronic configuration of silver is, electronic configuration is krypton 4d10 5s1. Now you can see there is no unpaired electron in the d orbital in the ground state, but still silver is considered as a transition element. What is the answer? Because in the common oxidation state, which is +2, what will be the electronic configuration of silver? If you remove 2 electrons, Ag2+ means the configuration will be krypton. 2 electrons are removed. First the electron will be removed from s orbital, second electron will be removed from 4d orbital, so the configuration will be 4d9. So you can see that silver has incompletely filled d orbital in its +2 oxidation state. So we can call silver a transition element. Now next is question number 6. Copper atom has completely filled d orbital in its ground state, but it is a transition element. Why? Again, we have to write the electronic configuration of copper. The electronic configuration of copper is argon 3d10 4s1. Now, in the ground state, the d orbital is completely filled, whereas in the oxidation state, common oxidation state, there is +2. So, Cu +2, the electronic configuration will be argon 3d9. In the common oxidation state, copper has unpaired d electron, which makes it a transition element. Now, the next is, what is the general electronic configuration of transition elements? So let's write the general electronic configuration. General electronic configuration of transition element is n-1 d 1 to 10 ns 1 or 2. Okay, so n-1, we know that the last electron enters into, this is the penultimate d orbital. Penultimate, or n-1d is the penultimate shell. So the last electron in d block elements enters into the penultimate orbital, which is n-1d. So the general electronic configuration of d block element is n-1d 1 to 10 ns1 or 2. It is written as 1-2. Okay. Now this is the general properties of d block elements. Now next, let us discuss the physical properties of transition elements. Physical properties. Now, physical property, the first physical property is that these transition elements, they have characteristic properties of metals, and you know the properties of metals. The properties are the transition elements like metals, they have high electrical and thermal conductivity, they have high melting point and boiling point, they have high tensile strength, they are malleable, ductile and sonorous, and they show metallic luster. So, they show the properties of metals. Now, again you can see transition metals, they can form metallic bonds. Okay, so these transition elements, they form metallic bonds. And greater the number, this is something very important, greater the number of unpaired d electrons greater is the interatomic interaction. Greater will be the metallic bonding and stronger is the bond. So this is a very important point to be noted. Now I told you the transition elements, they form metallic bonds. So greater the number of unpaired electrons in the d orbital, greater will be the interatomic interaction, or greater will be the metallic bonding, and stronger will be the bond. Okay, so as the number of unpaired electrons in d orbital increases, we have a very strong metallic bonding present in d block elements. Now next we have a question. The question is chromium is a hard metal. Why? Chromium electronic configuration is argon 3d5 4s1. Now why chromium is a very hard metal? Because chromium has 5 unpaired electrons in d orbital and 1 unpaired electron in s orbital. So chromium is a hard metal because as the number of unpaired electron increases, stronger is the metallic bonding. Chromium is hard. Now the next question, zinc, cadmium, mercury are soft metals. Why? So zinc, cadmium, mercury. We know the electronic configuration of zinc, cadmium, mercury. The general configuration is N-1, D10, NS2. Now why are they soft metals? Because there is no unpaired electron in the d orbital, so they behave like soft metals. So these are the physical properties of transition elements. Now next let us see the properties, other properties like melting point, boiling point, atomic radii, etc. of the transition elements, and how they vary along the period and down the group. So let's see the first property. Roman numeral 1 is variation of melting point and boiling point of transition elements. Now let's see how the melting point and boiling point vary for transition element. So from left to right across each transition series, when you move from left to right, we can say that from left to right, the melting point and boiling point will increase. First increases, then reaches a maximum value for the middle elements, because middle elements have maximum number of unpaired d electrons, and then decreases as pairing of electron take place. Because we know when you go in the first transition series, first what happens, the number of unpaired electron increases, and towards the middle of the series we have more number of unpaired electrons. After that what happens, pairing of electrons take place in d orbital, so the melting point decreases. So how do melting point vary along the period or from left to right in this transition series? First, the melting point increases, reaches a maximum value for the middle elements, because middle elements have maximum number of unpaired d electrons, and then decreases as pairing of electrons take place. Now when we compare down the series, different transition series, that is 3D, 4D, 5D, 6D, we can see that the melting point and boiling point increases. So next, down the series, we can say melting point and boiling point increases. Now the reason for this is due to strong metallic bonding. Strong metallic bonding in heavy transition elements, means down the group we have higher or heavy transition elements. So down the group there is a strong metallic bonding, so melting point and boiling point increases down the group. Now there is an exceptional case here which you have to note. Two elements that show anomalous behavior in their melting point and boiling point is manganese and technetium. Technetium symbol is Tc. So manganese, you know, there are 5 unpaired electrons in the d orbital of manganese, but this manganese and technetium, they have low melting point. So these are two elements that show anomalous behavior in melting point, manganese and technetium. Now in the transition elements we have the tungsten. Tungsten, whose symbol is W, which has the maximum melting point. So the element with maximum melting point in the transition series is tungsten. Now next comes a question. Zinc, cadmium, mercury have low melting point. Why? Because zinc, cadmium and mercury, you know that their electronic configuration is N-1 D10 NS2. Since there are no unpaired electron in d orbital, there is a weak metallic bonding in zinc, cadmium, mercury, so they have very low melting points. Okay, now next we are going to see a term here, enthalpy of atomization. Next, what do you mean by enthalpy of atomization? Enthalpy of atomization denoted by delta HA, or you can also denote it as delta H atom. Enthalpy of atomization. So how will you define this enthalpy of atomization? It is the heat energy required to convert 1 mole of a substance in its stable state to its gaseous state. For metals, it is same as enthalpy of sublimation. Enthalpy of sublimation means heat energy required for the conversion of a solid into gaseous state. And we know these transition elements, they are all in the form of solids. They are metals, so they exist as solids. So enthalpy of atomization is the heat energy required to convert 1 mole of a substance in its stable state to its gaseous state. So for transition elements, we can call this enthalpy of atomization as enthalpy of sublimation also. Okay, now next we have a question. Compared to 3D series, 4D and 5D series have greater enthalpy of atomization. Why? So 4D, when you compare 3D, 4D and 5D, who has greater enthalpy of atomization? 5D greater than 4D greater than 3D. The enthalpy of atomization is in this order. Now why this order? This is because you know that down the group, 5D means we have the heavy elements, heavy metals present, and there is strong metallic bonding present in heavy metals, which makes the enthalpy of atomization high for 5D series. Now next question. Why do transition elements exhibit high enthalpy of atomization? A very important question. Why do transition elements exhibit high enthalpy of atomization? The answer is due to large number of unpaired electrons. They have strong metallic bonding resulting in high enthalpy of atomization. So since there are large number of unpaired d electrons, there is strong metallic bonding which results in high enthalpy of atomization. Now the next question is, in the series scandium to zinc, they are the first transition series, scandium to zinc, the enthalpy of atomization of zinc is the lowest. Why? What is the answer? Because the electronic configuration of zinc is argon 3d10 4s2. So, since there are no unpaired electron in the d orbital, the electron from d orbital will not take part in metal bond formation. So, enthalpy of atomization of zinc is the lowest. So, with this we completed our melting point and boiling point. Now, the next property that we are going to see is density. So, next is Roman numeral 2, where we have the property density or variation of density. Now, you know the expression for density. Density is equal to mass by volume. And you know, along the period or across the period, that is from left to right, we know that atomic mass increases, but size means what? Volume decreases. So, you know that density and volume are inversely proportional. So, as size decreases, density increases. So, from left to right we have density of the element increasing because volume or size decreases. Now, the two elements which are most dense in transition series is osmium and iridium. Osmium, the symbol of osmium is OS, and iridium. Iridium symbol is IR. These are the two elements in the transition series which are mostly which are the most dense elements. Now, the lowest density element in the periodic table is scandium. Scandium has the lowest density in the transition series. So, this is about density of transition elements. So, we completed two properties, that is variation of melting point and boiling point, and the second property, that is variation of density of transition elements. Thank you.